Feel free to get started whenever you're ready.
Thanks. Yeah, let's do that then. So hello, everyone. Thank you for joining me today. I'm David from Voltron Data, and today I'm going to be talking about Apache Arrow, a bit about what it is, what its history has been, what some of its success stories have been like, and also where it's going to go in the future. So I am a PMC member and committer for Apache Arrow, so I'm on the governance committee and contribute to the C++ and Java subprojects. So Arrow, as you'll see, is a lot of different things, but at its core, Arrow is a specification for a memory format for tabular data. So let's break that down a bit. We have a table of data, a few columns, a few rows, and we want to figure out how to represent it in memory. Arrow specifies how to do that. It defines what the possible data types are, how to represent values of those data types, and how to represent arrays of those values. Arrow is a columnar format, which is something you've probably seen a lot in this conference. But just to go over it again, a columnar format is going to slice that data table vertically into buffers instead of horizontally. A columnar data layout has several benefits. Adjacent values are of the same type, so that generally works better with your processor's caches. And if you can take advantage of things like SIMD or vectorization, a columnar layout works better with those as well. Arrow is also generally designed to be zero copy. For instance, since every application, every language that uses Arrow agrees on the layout of the values in memory, that means you don't have to copy or convert data around anymore. You don't have to convert between different language or library-specific representations. You can just pass around pointers to the Arrow data, knowing that everybody will know how to interpret them. Arrow is pretty flexible and supports lots of different data types. For example, integer and floating point types, different date and time types, strings, binary data, and so on. It also supports nested data, so you can represent more hierarchical schemas as well. But of course, that's not all Arrow is. Arrow also defines other specifications. For example, there's IPC specification for when you do need to serialize data to store on disk or something like that. The IPC specification, for example, defines the Arrow file format for that use case. And just to go through that quickly, the Arrow file format is a binary format. Its key feature is that the layout of data on disk is essentially the same as the layout of data in memory. That way, you can just memory map an Arrow file and start working with the data, which makes it easier to work with larger than memory data. But of course, it also supports other features you might want from a tabular data file format. It has a footer, so you can get random access to chunks of data. It supports compression to reduce the storage requirements. And of course, it carries a schema so that your application doesn't have to be like Excel and try to guess whether something is a date or the name of a gene. But of course, more than just the specifications, Arrow also includes implementations of those specifications. Arrow is a set of libraries. But these libraries don't just implement the core specifications, they also implement higher level building blocks for applications to use. For example, as just a quick few examples of that, the Java libraries have an adapter for JDBC, so you can pull Arrow data out of a JDBC connection. The C++ libraries include implementations of different file formats like Apache Parquet, CSV, new line delimited JSON, and so on. The Python bindings PyArrow include support for converting between Arrow and Pandas data frames. And the Rust Arrow project actually even includes a distributed query engine. So as you can see within the Arrow libraries, there's also a lot of higher level functionality available out of the box. So that's a brief explanation of what Arrow is, but let's dig a bit deeper and look at how that actually plays out in practice. So here I'm going to give a tour of a bit of the history of Apache Arrow, so some of the key milestones, and also some interesting success stories. This is going to be a pretty brief overview, so where possible, I've included links for you to dig into if you ever want to learn more about any of these use cases. Starting at the beginning, so Apache Arrow was first announced in 2016. It was co-founded by Wes McKinney and Jacques Nadeau, but from the beginning, Arrow was a community project. They were joined by developers representing 14 major open source projects for the initial development. And as you can see from some of these initial blog posts, they're also supported by organizations like Cloudera and Dremio. The reason why these different developers came together for Apache Arrow was because they were facing a common problem. Many of these developers across their different ecosystems realized that a calmer data representation would be beneficial for their applications. They could make better use of their hardware. They were starting to reach limits. And of course, again, we've seen a lot about why calmer data is so useful. But at the same time, they were also facing some challenges with getting their different libraries, their different ecosystems to interoperate. Because each of their projects had different memory representations in different formats, they were facing a problem of having to copy and convert data between different applications to get them to interoperate. And they were seeing that that was actually adding a non-trivial amount of overhead. And so they realized not only a columnar representation, but a common representation could help eliminate or get around these problems. So Arrow was created to get ahead of those problems. For example, one of the first applications of Apache Arrow was actually in Apache Parquet. So just in case you're not familiar with Parquet, it's a tabular data file format for storing data on disk. It supports basically every feature you might want from such a format. It has lots of different encoding and compression schemes to reduce the data size. It has a lot of metadata so that you can apply filters and read only subsets of the file that you need, reducing your I/O costs, and so on and so forth. But with Parquet and other file formats like CSV and Apache ORC, developers were facing a problem when trying to bring these to more users, more ecosystems. If you have a bunch of file formats and you want to use them from C++ and also from Python and R and other ecosystems, naively, that means you have to do a quadratic amount of work. You have to implement the file format multiple times or implement bindings to that file format multiple times. You have to validate the implementations and bindings. You have to optimize any conversions between different data formats. If you're using a language like Python, that often means you're going to be passing through Python objects, which is going to slow you down and add overhead, and so on and so forth. So the motivation for adding Arrow to Parquet was to, again, work around this problem. Instead of building a Parquet to C++ project, and then a Parquet to Python project, and then a Parquet to R project, instead the Parquet project could build a Parquet to Arrow project, and then just use the Arrow bindings for each language. That way, we're not doing a quadratic amount of work. If we need to convert between representations, say if we want to use pandas in Python, we can then focus our efforts just on the Arrow to pandas conversion, which can then be used in other projects. And we'll actually see that coming up several times here. For example, Apache Spark was another early user of the Arrow project that also benefited from that Arrow and pandas integration. So with the previous use case, that was mostly relying on the memory formats that we could share data within a process. Spark wanted to share data between processes. Spark adopted Arrow because they wanted to implement or optimize their user-defined function implementation for allowing PySpark users to define UDFs. They had an implementation, but the problem with that implementation is that it was row-based and had a lot of overhead. So they had a lot of overhead converting from the Spark data representation to something, serializing that to something Python could read, and in produce, and they have to pay that overhead on every row. When they adopted Arrow for this use case instead, Spark could serialize a whole batch of data at once into Arrow arrays, pass the Arrow arrays to Python using the IPC specification, and then load a whole bunch of data at once into Python. They could then use the Python Arrow and Pandas integration that we just talked about to convert the data into a Pandas data frame to allow Python users to use a familiar API. And as you can see, the results speak for themselves. Comparing the prior implementation to the Arrow-based implementation, we saw as much as a 200x speed up compared to before. And again, any work that one project put into the Pandas to Arrow conversion could then be shared between between both projects or any other project using that same conversion. Of course, the Arrow project itself was also growing during this time. So Arrow started off with implementations in C++ and Java, and also got bindings or an implementation in JavaScript early on. But in 2018, contributors added Arrow libraries, Arrow implementations for Rust and Go as well. So what we're seeing here is that Arrow was starting to be used in more ecosystems and in more languages. Today, Arrow is supported in a wide range of languages. Since then, we've also added C# and Julia. There are bindings for Ruby and Python and R. So whatever language you're using, you likely have access to Arrow. So here's another integration that's different from the ones that I've talked about before. In 2018, NVIDIA announced a project called Rapids. Rapids is an open source suite of software for doing data analytics and machine learning on GPUs. So Rapids also chose to integrate with Apache Arrow, but instead of just using it as a serialization format or as a way to pass data around, Rapids decided to adopt Apache Arrow at the core and use the Arrow memory layout for all data processing on the GPU. So Arrow was providing two things here. The Arrow provided a memory layout that's efficient not only for CPU execution, but also for GPU execution. So as you can see, Arrow or columnar layouts in general can take better advantage of hardware. And by using the Arrow layout in particular, that meant that they could more easily share data between the CPU and GPU. They didn't have to add an extra conversion step when transferring data between devices. That step is already pretty expensive in applications, so there's no reason to make it even more expensive. Again, the Arrow project itself was gaining functionality during this time as well. So in 2019, development started on a project called Arrow Dataset. And I want to highlight Dataset because it's more of a user-facing API that, say, a data scientist might actually use in their work. So as I mentioned before, the Arrow libraries do more than just implement the specifications. They also implement higher level functionality, like implementations of Parquet, CSV, and so on. So in the C++ libraries, Dataset provides a abstraction over these file formats and over a file system I/O abstraction. It lets you read a large data set comprised of multiple files that might be stored on a local or remote file system as a stream of Arrow data. And then that data can be processed in Python or in R or anything else with bindings to Arrow dataset. For example, you could read a set of Parquet files with partitioning from Amazon S3, or you could read CSV files from Google Cloud Storage, or you could read those files from local disk as well. As an example of what this enables, there's a code sample here that demonstrates the Arrow R library. So we first use the Arrow R library to load a data set, but then we're actually going to use dplyr to process the data. Under the hood, those dplyr calls actually get translated into Arrow calls that evaluate these aggregations and filters using another component of the Arrow C++ library called AceArrow. So that means that a data scientist, a user, can use the APIs and tools that they're familiar with, but gain all the benefits of the Arrow project. In this case, that means they can do aggregations and filters and joins and so on over larger than memory data sets, over remote data sets using the same API that they already know. So if you want to learn more about this project in particular, I'd just like to highlight that there's a workshop constructed by one of my colleagues, Danielle Navarro, that walks through all of this. Arrow was also expanding into different domains during this time. So also in 2019, the Arrow project announced a new specification called Arrow Flight RPC. And this was intended for sending Arrow data across the network. As the name implies, Flight RPC is an RPC framework that's specialized for sending streams of Arrow data. It builds on top of gRPC and protobuf, which are pretty well-known technologies, and just optimizes their usage so that we can avoid unnecessary data copies in that stack and transfer Arrow data as quickly as possible. So this was intended to provide a low-level building block for applications to use, and we'll see some usages of that later on. So in 2020, about 4 years after the initial announcement, Arrow finally announced version 1.0. And as you can see, in some sense, version 1.0 wasn't a big milestone. Arrow had already been adopted by several different projects. It already gained implementations in multiple languages. It already started developing a wide variety of functionality. So 1.0 was more of putting a bow on everything and saying we're going to declare this stable, and we're going to declare this as a foundation for applications to keep building on, making a commitment for the future in some sense. And as you can see, the Arrow project had already been adopted by users as well during this time. In 2020, the PyArrow project, the Python bindings were reaching about 5 to 10 million monthly downloads from PyPy. Arrow continued to be adopted by different organizations. In 2021, Streamlit announced that they were adopting Arrow for their project. So Streamlit is a way to build interactive web apps that work with data using Python and pandas. That means that they need to transfer Arrow data from their Python backend to a JavaScript frontend. Previously, they had a custom serialization format, but in switching to Arrow, they gained two things. They managed to speed things up about an order of magnitude, and they realized it was easier to support new features in pandas. Again, they could reuse that same Arrow to pandas integration that other projects had been developing and using this whole time. That way, they didn't have to reinvent the wheel and could benefit and contribute back to all of the work that had already been done. Other projects, of course, were continuing to integrate Arrow. So DuckDB, if you're not familiar with it, is a embeddable analytics database, embeddable OLAP database. So kind of the same idea as SQLite, but focus on OLAP use cases using a columnar memory layout internally. They don't use Arrow directly, but in a case of, I would say, convergent evolution, their internal memory layout is almost exactly the same as Arrow's. So they added APIs that you could export result sets as Arrow without having to copy the data, and also run queries over Arrow data, again, without having to copy the data into DuckDB. And this was formalized by another Arrow specification called the C data interface, which is just a set of C function prototypes that kind of formalize how different components in memory can transfer streams of Arrow data to each other and report the Arrow schema and things like that. So what I want to highlight here is kind of the beginnings of like an Arrow native ecosystem. We have these projects that integrate with Arrow in multiple different ways and that you can compose, again, using Arrow. So looking at the code example here, it actually highlights 3 libraries. So there's DuckDB, there's the PyArrow dataset library, and there's also a project called Polars, which is a Python data frame library that uses the Arrow Rust library. So the code sample starts by loading a dataset of Parquet files with partitioning using the Arrow dataset library. It then passes it to DuckDB and runs a SQL query over it to do filtering. And it takes a result set and passes it to pollers to do an aggregation. So the thing is, these three projects didn't have to explicitly integrate with each other. They didn't have to build out special support for each other. They could just integrate already because they all use the Arrow memory layout. And I just want to wrap up this retrospective part with the latest version of Arrow, Arrow 10.0, which came out just a few weeks ago. And as you can see, the Arrow project has continued growing, has continued being adopted now with nearly 70 million downloads per month just for the Python bindings alone. So we started off in a world where different ecosystems would have to do a quadratic amount of work in order to all interoperate. But instead, by adopting Arrow, we can reduce the amount of work by settling on a common standard for data transfer. And we're also seeing ecosystems adopt Arrow more deeply at their core. So we said that Arrow is a memory format and Arrow is a set of libraries. But again, I want to highlight that Arrow is really an ecosystem. There's a whole bunch of projects, a whole bunch of impressive projects that let you get Arrow data in and out, that use Arrow data internally as their memory layout, or that use the Arrow libraries to help implement their own application. So with that, I want to continue highlighting some more use cases of Arrow, but ones that are more recent and ones that are still taking off. So these are going to be more different niches. These are going to be different domains that we're now seeing Arrow be used in with newer projects. So first one is a project called, is actually a pair of projects called GeoArrow and GeoParquet. And as the name implies, these are focused on geospatial data. They're not new data formats, but instead they're specifications for how to encapsulate geospatial data in the Arrow memory layout, in Arrow files, and in Parquet files. And the reason for this is that this gives the geospatial community an efficient memory layout to use, which is Calmer, which is the Arrow memory layout. So as you can see from this quote here, one developer found that the GeoArrow layout, the Arrow memory layout, made it easy to efficiently render geospatial data on the GPU, again, because that Calmer memory layout is already basically the layout that they need for GPU rendering. And so if you want to learn more, I've linked a demo that this quote comes from. I've also linked a blog post from one of my colleagues, Dewey Dunnington, that goes into the motivations and goals behind these projects. Another thing that you might have noticed is that a lot of the Arrow applications have been related to databases, but I haven't really talked about specific applications of Arrow to databases. That itself is changing as well. So relatively recently, within the past year or two, the Arrow project has adopted a new specification called Arrow Flight SQL, which provides a client-server database protocol that is Arrow native. I just want to point out it's not a SQL dialect, despite the naming, it's a protocol. So it defines how to send queries to a database and get back the results as a stream of Arrow data. Under the hood, it takes advantage of Arrowflight RPC, which we mentioned before. So the goal behind Arrowflight SQL is to help solve a dilemma that I think columnar databases might be facing. So you want to support, of course, all your different clients, including clients who might be using APIs like JDBC and ODBC. Building out drivers for all of those APIs is a lot of work. So some projects implement their own custom APIs and just pay the cost of implementing drivers or directing users to use custom SDKs. Other projects do things like re-implement the Postgres wire protocol to gain access to and compatibility with those existing drivers. But that also has downsides, especially if you're a columnar database. That means you're going to be transposing your data into rows just to send it over the network. And if your client is working with something like pandas or ibis and wants columnar data, then your client's going to be transposing that data right back. So that's a lot of wasted effort for practically no gain. So the idea behind Flight SQL is to provide a protocol that's intended for implementation by multiple databases. It uses Arrow data under the hood so that you don't have to transpose your data. And it also provides driver implementations so that you don't have to build them out yourself. For example, Dremio recently contributed a JDBC driver implementation to the Arrow project. And in this demo here, I installed that JDBC driver, loaded up dbeaver, connected to a Flight SQL demo server, and ran a query using a JDBC driver. So the promise behind Flight SQL is that it's one protocol that you can implement to support all of your clients. On the flip side, clients face a similar dilemma. So if you're an Arrow native application that wants to work with databases and wants to work with Arrow data from multiple databases, again, right now you have to do a lot of manual legwork. You have to take JDBC and ODBC and convert data from them. You have to build out bindings to a bunch of individual vendor SDKs. The goal of ADBC is to solve this problem analogously to how JDBC and ODBC solve that problem for kind of like OLTP based interaction patterns. So it's one API, it's an API standard. It's one API standard that an application can build against. That's then implemented under the hood by a set of drivers for different backend databases to speak whatever actual network protocol is necessary, convert the data if necessary, and give Arrow data back to the application. So if you're talking to an Arrow native database that has an ADBC driver, the idea is that you don't need to convert data at all, and you'll just get past Arrow data back. If you need to talk to something like Postgres that doesn't support Arrow, that doesn't support Columnar data, that's no matter. The driver will convert the data for you before passing it back to you. Either way, your application, again, doesn't have to worry about what's underneath. So again, it's one API for multiple databases. The ADBC project is still very new. It was only started this year and still under heavy development, but there's some demos. You can go to the GitHub repository to learn more, but there's some demos of a work in progress Postgres driver, a work in progress Flight SQL driver, and so on. And as you can see, you can already use it in Python, execute a simple SQL query in Postgres, and get back an Arrow table as a result. Continuing that theme of databases, we've talked a lot about the interfaces to databases, but we're also seeing Arrow being used more in the core of these databases. So I talked about DuckDB already, but there are now several projects that implement query engines on Arrow-like data. So they can take a query plan with filters and aggregations and joins and such and evaluate it over Arrow data to give you an Arrow result. So there's Acer and Data Fusion, which are part of the Arrow project in C++ and Rust. DuckDB, of course, is a full SQL database, but you could embed it as well. And Velox is a C++ project from Meta that uses Arrow with some extensions. And you can think of these as kind of Arrow native cores for bigger projects. For example, Data Fusion is now being used in the InfluxDB project, and Velox is being used in multiple projects, as we'll see. So that's a lot about Arrow with databases. So I also want to highlight Arrow being used in some machine learning use cases as well. So here, I'm going to talk about Spark with XGBoost. Of course, XGBoost is a machine learning toolkit. It accepts Arrow data as input for training data. And what Intel found was that in a ML pipeline with Spark and XGBoost, a lot of the execution time, the majority of the execution time, was actually just converting data from the Spark representation into something that XGBoost could read. So first, Intel started by plugging Arrow into Spark so that the data would be loaded in an Arrow format and then passed to XGBoost. And what they found was that this basically eliminated the data conversion overhead and drastically reduced the overall runtime of that ML pipeline. And now Intel is taking the Velox project, again, an Arrow native embeddable query engine, and plugging it into Spark to accelerate Spark even further. So the end result of this is lower overheads for ML training. And again, note that Intel didn't have to do all the work here. They could take off-the-shelf projects already available from the Arrow ecosystem and plug it into Spark. Another ML use case or another ML case study is a new project called Lance. So Lance aims to provide a tool chain for doing computer vision. And the interesting thing here is that they're basically completely built around Arrow. They have a custom file format that's more efficient for the kinds of workloads that they're targeting. And internally, it uses the Arrow layout, uses the Arrow IPC format. Their Python libraries use the Arrow types, use Arrow data as the API. They have demos that use DuckDB and Pandas and Matplotlib, all using Arrow to pass the data around. So through Arrow, Lance was able to plug themselves into an existing ecosystem and give their users all the tools that they want, give their users SQL access, give their users data frames, give their users Matplotlib, without having to build out specific integrations for all of those, without having to reinvent the wheel in each of those cases. Instead, they could focus on just doing what they know best, while using Arrow to provide everything else. So I want to kind of wrap up now with just a summary of where I think Arrow is going. So we started off seeing Arrow as glue between different ecosystems, and that's still really important. But now with newer projects like Rapids, with projects like Lance, with all these query engines, we're now seeing Arrow as the foundation of a system as well. Not just using Arrow as a protocol, but as the interface that you work with, the primary interface that you work with to use these projects. And so in general, while we might have started off, again, seeing Arrow as an internal detail to a project, we're now seeing Arrow move up the stack, provide higher level building blocks, provide really complicated building blocks. The query engine, of course, is a lot of work to build, but providing these building blocks that applications can use to keep on building more sophisticated projects. So thank you all for joining me today. I hope I gave you at least an overview of what Arrow is and how it might be helpful to you. If you want to learn more or get involved, you can join the Apache Arrow mailing list. The mailing list address is linked from that page. And of course, I'm happy to take questions here as well. Thank you.
David, thank you so very much. We don't have any questions at the moment, but we have a few minutes to spare, so we can give them time to pop in if you'd like.
Sounds good.
A few comments are coming in. Awesome talk, and thanks. Well, David, it looks like you left everyone with answers and not questions. Thank you very, very much for your participation today and for the wonderful talk.
No, thank you for having me here.
All right, it's been a pleasure. We'll all head out and head on to the next sessions. Thank you.